Page 1 of the Honors Chemistry Practice Exam. First ones are names and formulas, formulas and names. I'm not going to spend a whole lot of time on them. If I was using things, I would obviously have my periodic table with polyatomics on the back. Here's a name to formula checklist. I don't know if we've used that much, but it does have the acid rules. Here is the formula to name. Helpful thing. Also has the acid rules. The naming acids rules are on the poster on the front board as well. First one, not an acid, so copper 2 sulfate. You have to know that it's copper with a +2, sulfate with a -2. That's a match made in heaven. CuSO4. Iron 3 chloride signifies that it's iron with a +3. Chlorine or chloride with a -1. So to crisscross, it's going to be 3 of those and only 1 of those. FeCl3. Sodium, chromate. Got to find sodium on the list. It's Na with a +1. I don't remember chromate off the top of my head. I'll go searching for it. Chromate is here. -2, CrO4 with a -2 charge. CrO4 with a -2. So it's going to take 2 +1s to balance off just 1, -2, Na2, CrO4. Nitrogen trihydride. This is a going from name to formula. Do you see the word acid? No. Do you see prefixes in the name? This one I do. This is yes. This is a binary molecule. We also would know if we looked at the bottom that binary or molecular compounds are nonmetals to nonmetals. It's a molecular needs prefixes. So when I'm looking at nitrogen trihydride, it's N with 3 H's. This is also known as ammonia. Down here, we're going the other way around. We have to name the following. You could use this formula to name. They show you the formula. You have to come up with the name. There's going to be questions like, does it start with H? If so, it would be an acid. But no, none of these right now are. So is the first element a metal or NH4? If so, then it's ionic, and if not, it's molecular. This is a little checklist you can follow to help you remember how to name these things. First one then, FeNO3. It starts with a metal, so we have to think charges and crisscross. Fe is iron. NO3 is nitrate. The one thing we have to understand, though, is this may need a Roman numeral. We're going from formula to name. Formula to name says that if we name the positive ion first, does it require a Roman numeral? It does, because iron falls over here, nothing above it, there's no charge. We have to tell people what the charge is. How do we know the charge? We kind of have to do a reverse crisscross. If it's iron tied to nitrate, we always know that iron is plus something. It's positive because it's a metal. Nitrate is NO3 with a -1. So we had FeNO3 taken twice. That must mean if we have 2 -1s, it's going to take a +2 charge. Roman numeral 2 goes there. Next one's not nearly as complicated. It starts with a metal. That metal's name is calcium. The last name is chloride. It's in a column. Calcium's over here in a column that's very predictable. No Roman numeral needed. This is chromium, metal. This is hydroxide. We have to tell people which chromium. How come? Because chromium also is a transition metal, not in a column that's predictable like these or these. It's chromium, so we have to reverse engineer this to figure out, well, if there's 2 of these, so it must require that it's a Roman numeral 2. Finally, this one, does it start with a metal? No. So this is a molecular compound. First name as is, sulfur. Last name has to end with ide, chloride. But we have to tell that there's 8, that's octa. Don't remember those prefixes? They are on the back of your periodic table. Some people might question, should we then put a mono here? If the first name needs a mono, you don't put it. If the last name needed one, you do. I didn't make up the rules, just got to teach how to follow them. Next section down is balancing equations, but it says you have to have diagrams, particle diagrams. I don't care if you want to balance it and then draw the diagrams, or you might draw the diagrams to assist you in balancing. I'm going to go through that process even though it doesn't really matter what comes first on these. They're telling me that there's an N tied to an O, so I need just a circle of an N, a circle of an O. This tell me this is an O2, so that would be an O tied to an O. It's going to make an NO2. I guess I'm envisioning the N in the middle, flanked by or surrounded by two oxygens. It's okay if it's not correct, but that's how I would envision it. There's no way we can start with 1, 2, 3 oxygens and only end up with 2. So apparently we had to start with more of one thing. Well, no, apparently we have to end up with more product than that. So if I draw myself another NO2, because that's the only product that's going to be is an NO2, uh-oh, now I have 3, 4 of them over here. So that didn't quite fix mine. So there's no way we can end up with 4 if we only started with 3. If we would just have plus, we have 2 N's. If we have one more N over here tied to an O, now we have the same amounts of everything. There's 2 N's on each side. There's 4 oxygens on each side. It took 2 of these. 1, 2. Only 1 of these. I don't need a 1 there. I could put it, but I don't need it. To make 2 of these. The next one is iron. Well, that's just an atom. A chlorine molecule. And it's going to make an iron 3 chloride. I'm envisioning with an iron in the middle, flanked by or surrounded by 3 chlorines. There's no way you can start off with 2 chlorines and end up with 3. So we need more of something. So what do I try to fix first? Well, if I start off with 2 and end up with 3, I know that I at least need another chlorine. But they come in molecules. You also can't start with 4 and end with 3. So I now have more chlorines, but I had to draw it. So I'm going to go over here and draw myself another FeCl3. So now I started with 4 and ended with 6, and that's not legal. So I'm going to put a chlorine here, and that's 2 of them. Hey, now that matches. I now have 6 chlorines on each side, but I have 2 irons on the right. So I need another iron. It's not connected. It's a separate one. I drew a grand total of 2 iron atoms. 3 chlorine molecules, and it made 2 iron 3 chloride molecules. Now for the ones about atomic radius. First one says, which atom has a larger atomic radius, beryllium or oxygen? Why? Include Bohr's models of each of your answers. So I'm dealing with beryllium versus oxygen. So step 1 might be that I just remember this, that when we go across from left to right in a row or in a period, that the atomic radius decreases. We can memorize that, but I'd rather we explain the logic. So what we're going to do is we're going to use Bohr's models to talk about why that might be. First one, drawing a Bohr's model for beryllium. Beryllium has 4 protons. We're drawing neutral atoms when we do this. Darn it. Beryllium has 4 protons, so that means that it has 2 electrons in the first shell, 2 electrons in the second. This is a larger atom than oxygen. Oxygen has 8 total protons and 8 total electrons. 8 protons, and then it's got 2 electrons here and 6 electrons here. So which one really has a smaller radius or a larger atomic radius? Beryllium has a larger atomic radius. it doesn't have as tight of a grasp on them. How come? Because 8 protons, which is a lot of gravity pulling in small electrons, pulls harder than 4 protons pulling in the electrons. They have the same number of shells, so we should predict that they're the same size, but with much more energy, much more gravity pulling them in, the 8 protons of the positive, it's going to pull them in a little bit. So I might draw that more like a 2 electrons, 6 electrons. Distance from here to here is less than distance from here to here, tiny little bit, gradual. The next one, it's not about beryllium or oxygen, it's about lithium and potassium. Similar sort of question. You may have just memorized, oh, as you go down, if you go down a family or a group, you can use them interchangeably, you have a larger atomic radius. We're dealing with lithium and potassium. It says, though, we need to draw a Bohr's model to explain it. This one's actually a little bit easier. Lithium, 3 protons, potassium, 19 protons. Lithium, 3 protons, so that means it has 3 electrons, 2 in the first shell, and only 1 in the valence shell. Potassium has 19 protons, so it's got 2 electrons in the first, 8 electrons in the second, 8 electrons in the third, that's a negative sign, and then 1 valence. So they're similar because they both have 1 valence, but the radius is much larger because it has more energy levels or orbitals. Which has a larger atomic radius? Potassium. How come? Because there are more energy levels which are further from the nucleus. Even though there's 19 protons trying to suck them in, when you add an energy level, it does so like an orbit of a planet and ends up much further out each energy level.